In the previous videos, we have learned about Gauss elimination process that we applied on a system of linear equations, and in the recent last lecture, we also tried to understand the matrix multiplication, the meaning of matrix multiplication, as in linear combination of rows. So if you have a matrix and you supply the right combinations for, then it can provide you, or the product will be the linear combination of rows of the matrix which is in the right in the multiplication. Okay, so let's now see the application of that, or using that, how can we do the Gauss elimination and Gauss Jordan into the matrices. Okay, so let us see, consider this is a system of linear equations that we have, and which can be written in this form, right? So if you write linear equation in this form, you can since like this is 2 4 5 times x1, this is 2 4 5 times x1, then there is 3 minus 2 5 times x2, and then there is minus 5 minus 7 5 minus 7 minus 3 times x3, which is equals to 182, right? So this is giving a sense that you can write the matrix equation as in this way. From these two things, because both of them are the same, this one and this one, okay, these two things, both of them are same. So what we can say is that the left part of the this part is exactly is equals to this part, and this is the some kind of an expansion. This is some kind of an expansion of this, and we say that the linear combination of columns of coefficient matrix gives you B, right? So so we know that A is called coefficient matrix, X is a variable vector, and B is the constant vector that we want to make from the linear combination of columns of A, right? Okay, so this is our system of linear equations which can be transformed into a matrix equation of the form Ax is equals to B, wherein A is having all the coefficient matrix, all the coefficients, and the variable vector x contains x1 x2 up to xn, and the constant vector B is containing b1 b2 up to bm. Okay. Now since we see that while solving this equation, we go for Ax is equals to B. We have the matrix equation which can be solved, and we get X is equals to A inverse of B. Now this is involving two things, that is there are two things, two part to it, which we are going to do in this particular video. Is this that we want to find out the inverse, and then also we want to solve the system of linear equations. So these are the two objectives of this particular portion. Now just to have a recap, I just can tell you that you just once see the matrix multiplication, how does the matrix multiplication happens, and how it means. So especially when you look at the linear combination of rows, that is most important while doing the Gauss elimination or Gauss Jordan. So just take a brief view of it prior to proceeding any further. Moving ahead, so because this portion, whatever now we in this the notes, so this is all about matrix multiplication, which you need to understand what is matrix multiplication, how does it work. which we have covered already in the part 4a. Now look at this again. Come back to the system of linear equations. Ax is equals to b. Here, since we know that we have to do the same operation on the both side of equality. So what we did, we have taken a augmented b. So this is b vector. This is coming from the b part, and this is the coefficient matrix. So both can be combined, and then we can apply the Gauss elimination or Gauss Jordan so as to get uh, the solution of the system of equations. Okay, so again moving ahead, so let us see that we want to solve that system of equations. So now we want to see what thing should be pre-multiplied, because we are doing a row operation on this particular matrix. We want to do the row operation on this particular matrix. So when we try to generate the linear combination of rows, we need a matrix over here, and the matrix should be in such a way that it should be able to perform the Gauss elimination. So for example, if you want to eliminate this, if you want to make this 0, so what you want to put, the first row should be as it is. So the first row gives you 1 0 0, and the second row is, you just want to add the first row into the second row. So the first element will be 1, the second element will be 1, and the third element is 0. And this will if you do this, because what it's doing, this is 1 times first row and 1 times second row will be the second row of the product matrix. If you do that, then this 0 will appear. Once this 0 will appear, everything is fine. So what you want, you are drawing that the third equation is replaced by 2 times the first equation, third equation minus 2 times the first equation, and that's how you get the second set of equation, system of equation. So this is something which you need to do to perform the Gauss elimination. After doing the Gauss elimination, you get this kind of a matrix. Notice that in this matrix is something like upper matrix and b augmented. So this is not b exactly as the previous one, it's b dash. So because you did the some Gauss elimination, because of which the earlier b has changed and it has changed to a new b called b dash. Now once we have arrived to this, we can apply back substitution. We can apply back substitution to get the results. So this is one way, and we see that we can perform the Gauss eliminations first and then back substitution to get the result. Okay, so there are few terminologies that we want to define now. So one is called pivot. What is pivots? Pivots are the elements, the first element of a non-zero element of any row is called pivot. So here it is 1, here it is 4, okay, here it is 4, and in the last row it is again 1. So 1 4 1 are the pivots in this particular matrix. So the leading coefficient of a row, or unit first non-zero number of the row from the left side, is called pivot element. And the row echelon form. So there are two forms. One is row echelon form, and another is reduced row echelon form. Now a particular matrix is said to be in row echelon form. There are two important conditions. The first thing is, all the rows which has zeros everywhere should come at the last, right? should come at the last. And the second one is the pivot of any row should be on the right side of the pivots in the upper rows. So wherever you have the pivots earlier, so the pivots in the lower rows should be on the right side. Okay. So these are the two conditions. For example, if you can see that, okay, this first example, this is not in row echelon form because there is a row in the middle which has all the zeros. It should come at the last, then it can be a row echelon. Then it can be in the row echelon form. In the next example, one pivot in the third last row, the pivot is or the element which is leading non-zero element is in the row which is left of the previous row pivot. The pivot of the previous row's position, it is in the left side in the next row, which is not allowed, and that's why it is also not an echelon form. But it can be made into echelon form by making or by eliminating this the lower one. So the lower one we can eliminate, and we can do something like row 3 minus row 2. If we replace row 3 by row 3 minus row 2, this item becomes 0, and then it becomes the in the row echelon form. This is quite a possibility. Uh, so, anyways, example 3 is in the row echelon form because all the both the two conditions are met. So, what you get? You get that all the zero, so there is all the zero elements here, and that is coming in the last row, and every pivot is in the right side of the previous pivots. So like 3 is in the right of 2 and 1, 2 is the right of 2 is in the right of 1, so that condition is also met. So this is in the row echelon form. Now there are certain things related to the pivot elements and the means free variables. So what is that? So variables corresponding to the columns, because this every column is corresponds to a particular variable. Every column corresponds to a particular variable. So the variables corresponding to the columns which contain pivot elements are called basic variables, and the variables corresponding to the non-pivot columns are called free variables. So basically, which is not a basic variable is a free variable. These free variables accounts to the infinite number of solutions, and the pivot variables accounts to the particular solution or a special solution, which is uh, which is generated by the pivot variables. So when we want to generate the particular solution, we set all the free variables 0 and get the values of the basic variables. While in case of uh, free variables or the homogeneous solution, so homogeneous solutions, how do we get it? We say that okay, we have a particular solution, and then we want to add all those solution to it which generates 0 when it multiplied by a. So ax particular plus ax homogeneous will give you b plus 0 will always be satisfied. So homogeneous solution can be common to every solution for any b, and the particular solution is actually dependent on the b, what b you have. So this is the two things, like particular solution, and we have another one which is called homogeneous solution. And the final the total solution, because we what we want to find out all the values of the variables which gives us the desired b vector. So that particular solution is called total solution, collected by clubbing these two solutions, the homogeneous solution and the particular solution. Just let us see one example about it. So this is the system of linear equation. We did some row operations, and we get this one, we do again some row operations, and and we reach to this particular system of linear equations, this particular system of linear equation. So it has 2 and 7 as pivots. The rest two rows are completely zero, are below uh, the last in the matrix. So this is in the row echelon form. Now we can solve it by first by putting x3's value 0. So this is corresponding to x3, this column is corresponding to x3, and we can put the x3 0 and solve it for x1 and x2. And that's how you get the particular solution. So in first row, you can see the first non-zero entry is in column 1 and the second non-zero entry is in the column 2. So that you can see here. Then the pivot variables x1 and x2 are there. x3 is a free variable, and rest of the rows have 0 entries on the both sides of equality. So we are expecting here at least one solution. So so some solution we will get, and then there are certain free variables. Once we have free variables, we have a number of different solutions. So let us go ahead with this new system of equation. So as we said, the particular solution is found by setting the free variable 0. So once we set the free variable 0, we get the value of x1 and x2. Okay, we put that value in place and we get the particular solution. To find out the homogeneous solution, we put the things 0. Okay, just to show you here that we can get this solution 27 by 14 and this just by doing some processing again in the matrix. So the back substitution exercise can be done this way, that you do some row operation such that some row operation with the help of this 7 we can, okay, with the help of this element we can remove -3 and make it 0. So this is the row operation, desired row operation. If we do that, that thing becomes 0 and we get a new b, a new row, right? After that we can divide the first row by 2 and the second row by 7 to get this one, right? So in certain sense we get the particular solution because x3 corresponding to this particular column is 0. The value of x1, so let me take it a different color, and this 1 is corresponding to x1, and this will get 27 by 14, which is exactly equals to this part. And this another one with respect to x2 is giving the value 2 by 7, which which is coming exactly same here also. So you can do within the matrix also the back substitution, you can actually forget. And this method is called Gauss Jordan, which is generating zeros above the rows also. It's not only below the rows, it is creating above the row, above that particular row which has that pivot element, because of which we are generating the zeros in the matrices, in the matrix. Okay. So finally, what we are trying to say is that if you apply Gauss Jordan, you achieve this kind of format. You achieve this kind of format. Once you achieve this kind of format, since this I is corresponding to the basic variables, this free variables are corresponding, this f matrix is corresponding to the free variables, and this is the b. So I2 is saying that all the basic variables has this, the value is b21 in the particular solution. So we can say here, we can go ahead here and then see that what is going to happen. So somehow it should be something like this. We are interested in particular solution as well as the homogeneous solution. So if you just looking for the particular solution, we can write it like this. And we found that the particular solution, the the solution corresponding to the homogeneous system of solutions is given by minus fyf. Why we have divided the variable vector into two variables, xb and yf. So the xb is the basic variables, yf is the free variables. So once we have divided the free variables and basic variables, we, because of that matrix form, because of this matrix form which we have gone earlier, this part, this one, because of this matrix form, we are able to say that the, in case of homogeneous solution, we can get the basic variables value like this one. Okay. So finally what we get this way, that the value of x vector, this is equals to this one, wherein yf is belonging to some set. Yf is a vector, it can be r1, r2 or 3 depending on the number of free variables. So means the number of free variables, as much as number of free variables are there, yf has to belong to that particular Cartesian space. Now there is another thing called reduced row echelon form. Reduced row echelon form can be achieved by Gauss Jordan, which says that every matrix is in the, if it is in the reduced row echelon form, the first thing is that it should be in the row echelon form. The second thing, that all the pivots should be 1, and the third thing, the pivot is the only non-zero item in the column. Which means that we have done the elimination not only the below the pivot, but we have done the elimination above the pivot also. So it has created zeros entire in the entire column except at its place, and that's how you make a reduced row echelon form. So let us see what are the different operations that are allowed to us. We can actually swap the rows, which is a part of or kind of making the linear combinations, because swapping, you can take r2 times 1 and r1 times 0 to replace r1. So row 1 is replaced by 0 times r1 row 1 plus 1 times row 2, and it is trying to replace row 1 by row 2. So which you can do, and again replacing the particular row by a linear combination of rows. Okay, that is again what we have said, replacing a row by a non-zero multiple. So you scale just one row and then you replace it by itself. That you can do. It is again similar to the linear combination. It's a subset of linear combination, in fact. Swapping the two columns, now that is most interesting. When the swapping and why the swapping is allowed of the columns. So look at the equations if you look at the equations, you see that when you are trying to do, or when you are having this particular equation with x1 x2 x3, you can swap the columns, so but when if you are swapping the columns, you have to swap the variables. So if you want to swap x1, means the first column and the third column, you have to swap the x3 with x1. So for example, here this particular column is exchanged with this column. So accordingly, we have exchanged the position of x3 and x1 in the variable vector here. And nothing else has changed. It is exactly same as that, writing in this way, that x1 plus x2 plus x3 is equals to 5. Instead of writing this way, we are writing x5 plus x2 plus x1 is equals to 5. So we are just trying to exchange the position of the variables. So in the entire column, you have to change the position. So you can do that, which is allowed, but you have to change the variable position as well. And it does not change the system of linear equations, it remains same. So the idea is, when we want to Gauss elimination, we are knocked down, or making the coefficients 0 below the pivot elements. While we are going for the Gauss Jordan, we are making zeros above as well. While doing all that, we are doing only the row operations. But when we are trying to find out the particular solution and the homogeneous solution, what we need a special form of matrix. The special form of matrix looks like this one. This special form of matrix we want. To obtain this particular form, we can swap the variables, we can swap the columns, and correspondingly we have to swap the variables. Once we are able to do that, we are able to achieve this form of matrix. Once we are able to achieve that form of matrix, we can straightforwardly tell that the basic variables value is b21 vector, and the total solution can be given accordingly, because it's not that difficult now. Okay, so now if you are interested in inverse, inverse is nothing big. Inverse is nowhere big. So what we are trying to do, instead of solving for the inverse, let us or finding the inverse, we want to solve ax is equals to b for these three b's, b1 b2 b3. b1 b2 b3 are, you can see that they are very special values, they are columns of the identity matrix. And when we augment all this equation, this whole equation, we get this one. Now if we are trying to generate a inverse in the position of a, we definitely will be able to create a inverse in the position of I. And that's what we are trying to, the way we are trying to finding the inverse. Thank you. In the next video, we are trying to see vectors more formally.